the lesson for the article 1.2 of the book Mechanical Systems Calculations of the Marine Facilities textbook. The lesson determination of force vector projections when the force vector indexes belong to the same plane. This determination of force vector projections is important to find the balance conditions of the mechanical systems, and to find this force vector projections, first we have to define the projection of the force vector on axis correspond to the difference between coordinates of its end and beginning of the force end and beginning. So coordinate B projection on the axis X is x2, and the coordinate A is the beginning of the force is x1, and the projection of the force is the difference between these two coordinates x2 minus x1. And this projection of the force on the abscissa axis is more than 0 if x2 more than x1, and the projection less 0 if x2 minus x1. It could be if the angle between the abscissa axis and the force is more than 90 degree, and if the force have the opposite direction to the abscissa axis. The triangle ABC, we can consider ABC. The hypotenuse of this triangle is the force vector F, and this leg AC is the projection of the force vector to the abscissa axis. And this projection, we can find Fx on the abscissa axis as the product of the magnitude of the force F onto the cosine of the angle alpha between the hypotenuse and the leg. This means the projection between the direction of the force and the abscissa axis. I mean the alpha angle. This projection of force on the abscissa axis is more than 0 if alpha, this angle between hypotenuse and the leg of this right angle triangle, if this angle is between 0 and 90 degree. If this angle is more than 90 degree, like open angle, so the projection of the force on the axis is less than 0. That's if alpha is between 90 degree and 180 degree. And the projection of this force F on the abscissa axis is 0 if alpha angle is 90 degrees, if so mean that this alpha is right angle too. Examples of determining the projections of forces on a plane. We can consider the follow examples. The first, projection of the force F1 onto the abscissa axis. We can use the same rule, multiply the magnitude of the force F1 onto the cosine of alpha angle between this direction of the force and the direction of the abscissa axis. This angle is determined counterclockwise. The projection of F2 is equal to the magnitude of F2, so F2x is F2. This is due to the angle alpha of F2 between the force F2 and the direction of the abscissa axis. The angle is 0, and the cosine of 0 angle is 1, so the projection of this force on top of this axis is equal to magnitude of the same force. So the projection of the force F3 on the abscissa axis. The projection is the product of the magnitude of force F3 by cosine beta angle, open angle, we can see here. Or we can determine this as a product of minus F3 by cosine phi. Cosine phi is a angle of taking clockwise between the direction of the force and direction of the x-axis. So we use minus this easily because the cosine of a negative angle is negative, so So we have to consider the direction of the angle. The projection of force F5 on the abscissa axis is minus F5 because this force is in the opposite direction to the abscissa axis. And the projections of forces F4 and F6 are equal and equal to 0. And they are equal to 0 and to each other due to they are perpendicular, so right angle to the abscissa axis. That's why the cosine equal to 0 and the product of the projection of magnitude of each of the forces on the corresponding angle between this force, each one, and the abscissa axis. This cosine is equal to 0, so the projection of each of these forces on the abscissa axis is 0. And it's important is determine the projections of the force vector on the axis of a Cartesian coordinate system. This is when the force is not on the plane, but is special determination of the force in the space. The composition of force vector into the projections we can consider as the force F. We can decompose into 3 projections in tridimensional system of coordinate system Cartesian. So axis x, y, and z. The projections we have fx, fy, z. This projection we can consider as vectors lies on each of the axes. So the force vector is the sum of the vectors of each projections on the coordinate axis. Besides, we can determine the projection of the vector on each of the coordinate system as a magnitude of the projection multiplied on the unit vector of this any one considered coordinate axis. So I is the unit vector of the coordinate axis x, j is the unit vector of coordinate axis y, and the k is unit vector of the coordinate axis z. And this is the determining of the force by its magnitude of projections and the vectors units of the coordinate system Cartesian. The modulus of each of projection of force onto the axis on this picture on 1.2.3 is determined as the products. But it's important for this explaining that we use the concept of the direct angles, directed angles of the force related to the coordinate system. So alpha, beta, and gamma are the angles between the force vector and each of the axes of the coordinate system. Alpha between the force and the x, 0x. Beta is the angle between the force F and the axis y, and gamma is the angle between the force and the axis z. So each magnitude of the projection on each of the coordinate axis we can find as a product by magnitude of force on cosine of the corresponding angle. So projection of the force on the x-axis is equal to magnitude F multiplied cosine alpha. Projection magnitude of projection of force F onto the y-axis we can consider as a product of the magnitude of force on cosine beta and the projection of the force F on the z-axis we can find as a magnitude product of the magnitude of force F by cosine gamma. Only 2 angles of 3 considered alpha, beta, gamma angles in each couple between the force and definite axis of the coordinate system x, y, or z. Only 2 of them are independent. So when we use the known equation from the geometry and that the cosine in square degree of alpha plus cosine square degree beta plus cosine square gamma equal to 1. So we can define any of the cosine and any of the angle independence on two others. So, for example, on the picture 1.2.4, we can see the force and the rectangle with the force rectangle which in z-axis pass through, I mean the plane of this rectangle of the force vertical rectangle located parallel to z-axis, and z-axis lies in this rectangle plane. And we have the horizontal plane x0y perpendicular to the axis z and perpendicular to the plane of this rectangle. Rectangle fx, fxy, and 0. And so if we consider the projections in this rectangle on the plane parallel to z-axis, the plane of the rectangle fx, fz, fxy, and 0, we can indicate on this part of the picture. So we can find first the projection f of the force F on the axis Z as the product of the force magnitude on the sine of the angle phi. This we can here see. Fz is equal F multiply product of magnitude of the force by the sine of phi. And as well, we can find the leg, the horizontal leg 0 fxy. The fxy leg is the product of the force magnitude f product by the cosine phi. So we can find the fxy as a f product cosine phi. So in this case, when we have this horizontal projection of the force, horizontal means the projection of the horizontal plane x0, y located perpendicular to the axis z and to the rectangle fx, fxy, and phi. So having this projection fxy, we can find it is a product of magnitude of force f by cosine phi. So we can find the projection of this force on the axis x as a product of fxy by cosine phi. Cosine phi is the angle between this auxiliary axis 0u, or this is the same angle phi between the axis x and the plane which is located the rectangle fz, fxy, and phi, and the 0, sorry. So using this horizontal found projection fxy as magnitude of force, a product of magnitude of force by cosine phi, so we can next find the projection on the axis 0x as a product of found projection fxy by cosine of angle psi. As it here, and when we substitute all that into it, we can find fx as product of the force magnitude f by cosine phi and cosine psi. So, and next, another one projection on the axis y we can find as the force projected on the horizontal plane, finding the fxy projection, and next we do that use a sine function of the cosine of angle psi. So fy projection is equal to magnitude of product of magnitude of force by cosine phi. Cosine phi next, so we found the fxy, and next product by sine psi. By sine psi we can find fx, fxy. This leg is equivalent to projection of the horizontal axis 0, y, etc. So, and by this manner we substitute the determination of the force by its magnitude and triangles of its direction alpha, beta, and gamma. We did substitute this by the magnitude of force as well, and only two angles, phi and psi. So we exclude one of the angles. This is good for the mathematical transformations. The examples of determining the projections of forces on axis we can see on the picture 1.2.5. On this picture, we can find that for the examples, force F1, what is the projections on the axis x, y, z? We can see that the force F1x, F1 and is parallel to first axis due to this all forces located into the rectangle parallelepiped A, B, C. And so we can find that the sides of the parallelepiped, some of are perpendicular to the axes, and some is parallel. Some are parallel. So F1x projection of the force F1 on the abscissa axis is minus F1 because it's F1 force is in opposite direction to the axis 0x, and F projection on the axis y and on the axis z are zeros because this direction of the force F1 direction is perpendicular to both of the axes 0y and 0x. And the projection of the force F2, this was force F2, and this force lies in the plane parallel to the plane 0 yz, and so we can determine and perpendicular to the axis 0x. So the projection of F2 on the x-axis is 0 because this force is in the plane perpendicular to 0 x-axis, and the projection of F2 in the on the axis 0y and 0z we can find as the magnitude of the product of minus magnitude of force F2 multiplied cosine alpha. So we can find the projection on the axis 0y. This is due to this projection directed opposite to axis 0y. This we can see cosine alpha and the force F2 the projection have the opposite direction to the direction of the axis y. So we use the minus sign. And next is the projection of F2 on the axis Z. F2 projection F2Z is product of magnitude of the force F2 by the sine alpha, and the projection F2Z is in the same direction than the axis 2, so we have the plus sign or with no sign. And next we have the force F3. The force F3 projections are F3x on the axis. So first we decompose the force F3 into two forces, which resultant F3 is the first is the force is located on the this parallelogram. So F3x projection is product minus F3 cosine beta. Beta is this angle between this force F3 and the horizontal plane BHGC, this angle B, and we have the projection of this force F3 on the plane BHGC. And this force, next we use the angle between the direction in this plane of this force relative to the axis, x-axis. We use the gamma angle, and we product as well by the gamma angle, cosine gamma angle. So we find next the projection of force F3 First, we decompose this force to determine the component of force F3, which is parallel or perpendicular to each of the coordinate axes. And F3x is a product of minus F3 by cosine beta, this angle, and cosine gamma, the angle in the plane. And the projection of the force F3 on the axis y is F3y is equal to product of the magnitude of the force F3 by cosine beta. So we again found the projection of the horizontal plane. And next we use the sine gamma, and we found the projection of force F3 on the axis y. The vertical part of the decomposition of force F3 we did original, not important due to the vertical part. This from the point B to down here indicated is perpendicular to the axis y, and is opposite. So projection of this part of the decomposition of this force, this projection of this part of the composition have zero projection of the axis y, and the force projection of F3 on the vertical axis z indicated here is product minus F3 by sine of the angle beta. Yeah, this is understandable because if we decompose this force F3 into two parts, two components, the force is in the horizontal plane perpendicular to axis z, so any projections of the force F3 into the planes perpendicular to the axis makes the zero projection themselves on this axis, and the another one part of the decomposition parallel to the axis we search the projection for is in opposite direction, and so we use a minus, and this magnitude of this minus magnitude product of f magnitude of the force F3 by sine of the angle beta is this vertical part of the decompose of this force F3, and is parallel to the axis Z. So this way we can find the projections of the forces in the Cartesian coordinate system, a special Cartesian coordinate system. Questions and comments. Finding projection of force vector onto axis when the force vector and axis belong to the same plane. If the force and the axis belong to the same plane, we usually use the cosine of the angle between the force and the axis, and we took the angle counterclockwise if it's a positive angle. Determination of projections of force vector on the axis of the Cartesian coordinate system when the force vector does not belong to any of the coordinate planes. To determine projection of force vector on the axis of Cartesian coordinate system, we use the cosines of the direct angles of the force in these coordinate systems. Projection of each of the axis of the coordinate system in the Cartesian coordinate system is the on the each is the product of magnitude of the force on the cosine of the corresponding direct angle of this force vector, using double projection of the independent force vectors direction angles in a Cartesian coordinate system. So we have to take into consideration that only of three direct angles of the force vector and each of three axes of the coordinate system, only two angles are independent. So we can do a mathematical transform, and we can find the angles only two to reduce the number of the variables. This is positive to do the calculus and to do the to research the issues of statics and to simplify the force systems and to define the balance state of the mechanical system. Thank you.